Lal, she is telling that she is present. Okay, Srija, I have given attendance.
Thank you, sir.
So Chandana, I am calling once again. I don't see Chandana. So can I mark it as a absent? Chandana. I don't see in the list. Therefore, I am marking absent. And Subrat is one. And Malut, Sirisha is trying, but she is unable to do that. It's fine. Sham Sundar, I have given attendance. No, don't worry. And Amruta V is absent. And also, yeah, that's fine. I hope I am audible, right?
Yes,
Yes,
sir.
sir.
Yes, sir.
Okay. Well, good evening, students. Well, I think we will proceed our discussion on postulates. If I'm correct, this is the summary of the postulate number one, right? If I'm correct, in the last class, we have discussed the postulate number one. The postulate number one deals with the state function or the wave function of a system. And then wave function should a wave function is nothing but a simple mathematical function, and the mathematical function has to fulfill certain condition. Only then such a mathematical function can be accepted as a wave function in the quantum mechanics, okay, to describe the behavior of a system, okay. And those are square integrability, continuous continuity, and also single value. So this is where we have stopped in the last class. And if a mathematical function is not fulfilling even a single condition what is listed here square integrability or continuity or the single value, then we will not accept such a mathematical function as the wave function, right? So that's all about the first postulate. And today we will try to learn the postulate number second postulate and third postulate. We will try to understand. The second postulate statement is you can see on this slide. Corresponding to every observable, there is a linear Hermitian operator. Corresponding to every observable, there is a linear Hermitian operator. To find operator, write down the classical mechanical expression for the observable and make following replacements. One such replacement is that if there is a x, you have to replace with the x. The other replacement is that if you have a momentum component, then the momentum p of x has to be replaced with minus ih cross dou by dou x. Well, if you look at this, the entire second postulate statement, there are two parts. The first part we will try to learn and understand fully, and then we will go to the second postulate. So we can divide the complete statement into two parts. One is the corresponding to every observable, there is a linear Hermitian operator, right? So this is something that this one sentence or statement we try to understand first, and then we'll go to the next second half of the postulate. Okay, so corresponding to every observable, there is a linear Hermitian operator. Then what is observable, first of all, right? What is observable? So the observable can be anything. Okay, it can be anything, but which depends upon the position and the momentum of a quantum mechanical particle. Okay, and it can be anything. Okay, suppose you have you just consider a particle freely moving in one particular direction. Okay, a particle, our quantum mechanical particle, is moving in one particular direction in very freely. That means it doesn't have, there is no external force acting on the particle. Now, the observable means, observer is somebody who is basically observing this particle. Okay, what he is observing? He is observing the particle, freely moving particle. Okay, the observer probably interested in observing the position of the free particle, right? You have a particle and it is moving, and you may be interested as an observer. You want to know what is the position. What is the present position and what is the present position after some time. So therefore, the position of the particle is one observable. Similarly, okay, it is as it is moving, then it will have some momentum because it is already a particle. Therefore, there is a mass, and since it is moving, therefore, there will be a non-zero momentum, and the observer may be interested in observing the momentum of the particle. Okay, so momentum can be one observable. Okay, it can be called as a one observable. Similarly, the kinetic energy. Okay, we are interested in the kinetic energy, which is represented by px square by 2m. Please note that why I am writing px, because my particle is only moving in x direction. Therefore, its kinetic energy x component only we will consider. Suppose if it is having suppose if the system is moving in all three dimensions, therefore the kinetic energy will have three different components. Okay, of course you might be knowing this relation, how it has actually arrived, right? Half mv square is the kinetic energy. This is something that we all have studied, right? Half mv square, since it is x direction, that you can take the velocity, x component of the velocity. This is something that we represented with in a slightly different manner in the quantum mechanics. Half mv square is the formula that we normally know about the kinetic energy of any particle is given by If it is moving in x direction, it is given by this, which is nothing but actually px square by 2m. How this has come? Basically, this is nothing but basically you can multiply the numerator and denominator with m. Numerator and denominator with m. So when you multiply numerator and denominator with m, the net result, it doesn't change, right? So in the numerator, you have already one m is there, and there is m. Therefore, m square and vx square. Therefore, you can simply happily write mvx whole square. Mvx whole square divided by 2m. And mv is a momentum. Since we are having the x component of the velocity, therefore we replaced with the px. Okay, so this is replaced with the p shorthand notation, and in the denominator we have the 2m. That's how it has come. So don't confuse, and this will not be explained again and again. Well, that is a shorthand notation of the kinetic energy. We don't use the half mv square as such, but in a slightly different manner we will be using. And the second one, we may be interested in measuring the potential energy of the freely moving particle, right? In such a case, therefore, the potential energy can be called as a observable. And similarly, there are cases, where you may be interested in measuring or observing the total energy of the system, which is freely moving in one particular direction. In that case, the total energy is nothing but the kinetic energy plus potential energy. Therefore, that can be called as a one observable. Okay. Then, having known what are the observables, okay, observables are nothing but these are some of the physical quantities which are measurable in the laboratory. You can just remember. So observables are nothing but the some of the physical quantities of the particles which are actually which we can measure by doing an experiment in the laboratory. Okay, so just I have given few examples, but there can be many. You may be interested in rotational momentum. So rotational momentum, if you are interested in a system which is rotating around a fixed point, then it will have rotational velocity and also rotational momentum. So those can be again called as a observable. So observables are anything that we may come across in physics. Okay, these are actually real quantities. Those are something that we are interested in, because how a system is behaving, if you want to know, then the only possibility is that you have to measure these observables. Only then you will come across, you will understand the system. Now, in the statement, if you look at for corresponding to every observable, the continuation of the statement, the first within the first sentence itself, you have corresponding to every observable. So we learned what is observable. Then the continuation is that corresponding to every observable, there is a linear Hermitian operator. Linear Hermitian operator. So there are three terms. Let me try to explain what exactly is operator first, and then what exactly is a linear operator, then what exactly is a Hermitian operator. So having understand what is observable, then let us try to understand what is operator. Okay, operator is nothing but you have a function. Let us suppose that you have a function f of x, and you do something on the f of x. Okay, you are going to do something on the f of x, and that function will be basically transformed to a different function. Let's say it is a g of x. Okay, you do a function. Basically, you have a function. You started with the function, and then this function, you are going to do something on that function, and then naturally what happens when you are trying to do, then it modifies to some new function. Okay, so the process what you carry out on the function, the first function or the initial function, what we called as an operator. The process what we called as, what we do on a function is referred to as the operator. You can see here, uh, let's say you have f of x, and then f of x, there is a one a here, right? One, there is a is something, it may be, we will come to that what exactly is operator. So a is something acting on the acting on the function. Okay, a is something that acting on the function, and then it is transformed to a new function g of x. Okay, if this is the condition, then a is said to be operator. If this is the condition, then a is said to be operator. Okay, and to distinguish this a operator from rest of the normal letterings, normally we keep a special hat on top of the operator, any operator. So here I used a as a general thing, but you can use any of your letter. But anything if you want to represent as an operator in quantum mechanics, then we put a hat on that. What is the speciality? Because this guy is something that he is acting on somebody, and then as a result of that, basically that the function is transforming into a new function. Therefore we treat that the operator in a special way, and then we are keeping to distinguish a special hat on top of the operator. Okay, so let me show you what exactly is what exactly are the operators. Okay, so what are the operators that we come across? Okay, for which I have considered, there are two functions I am considering. There are the function that I am considering. F of x is equal to x square. I told you wave functions or the state functions that we come across in quantum mechanics are nothing but the mathematical functions. Therefore, I'm just taking two mathematical functions. One is x squared, the other one is the e to the power minus 2x, or the e raised to minus 2x. Okay, there are two functions I have taken, and there is an operator, there is a general notation for operator that I have given here, a. Okay, now what I do, I have two functions, of course. One function is x square. Okay, I will take the first derivative of the x square. I will take the first derivative of the x square. What is the first derivative of the x square?
2x.
Well, it is 2x. Very simple, right? Now, the d by dx, what we call it as operator. Okay, these are not very strange bodies. They are not the aliens. You all have studied mathematics, and if I give the example, then you really find it is very easy, and they are very much known to you. Now 2x is one operator, sorry, d by dx is one operator, and then the function, the original function f of x, when the operator operates on a f of x, that is x squared, then it transforms to a new function. Therefore the action what you are doing, we call it as a operator. Now when you take the first derivative of the second function, that is e to the power minus 2x, then it becomes minus 2 multiplied by e to the power minus 2x, isn't it, right? So this is, you can say the d by dx is one operator. Why? Because it is when it is acting on these type of functions, then they are transformed to new functions. Then I may be interested in taking the square of the functions. Taking the square of the function. Okay, that can be called as a one operator, because you have x square. Just to take the x square, square of the x square. Therefore, square of the x square is nothing but x to the power 4, right? So definitely the square is referred to as an operator. And similarly, if you take the square of the e to the power minus 2x, then it becomes e to the power of minus 4x, right? You may be interested in the second derivative. Why you are confining to the first derivative? You may be interested in the second derivative. So what is the second derivative of the x square? So it is quite obvious that the 2 is the answer, second derivative of the x square. And then what about that one? 4 into e to the power minus 2x is the second derivative of the another function. Okay. And sometimes you may be interested in just multiplying. Sometimes you may be just interested in multiplying the function, right? I just took 10 as a multiplication factor, but then you can take any number of your choice. It doesn't matter. But then the idea is that the operator is something that when it is acting on a function, that function must be transformed to a new function. Okay. So x square, when you multiply with the 10, then it becomes 10x square, and similarly 10 e to the power minus 2x. Then sometimes you may be interested in just multiplying with a variable that is x. Okay, even x can be called as a operator. Okay, in that case, then the first function becomes x cube, the second function become e to the x into e to the power minus 2x. Okay, I hope that you have convinced you already know these things, but then now there is a special name. These are actually called as the operator, the operations. There are so many mathematics that you have learned in your BSc till BSc. So what all you have learned now, there is a name, the action that you are carrying out on a original on function. We call it as a operator. That's all. So there is nothing. Of course, the definitions, my definitions are very simple, and because you are a chemist, and then therefore we should not go very complication. But then if you go to a mathematics person or a physics person, their definitions will be very different, but then the ultimate meaning or the concept is remain the same. Okay, they use different languages and notations, but ultimately operator is nothing but an action that we actually carry out on a function, and after the process of that action, then the function must transform to a new function. In that case, the action what you are carrying out on a function, we call it as a operator. Now please remember, in the statement we have uh, just a minute. Yeah. So in the statement, we have seen corresponding to every observable, there is a linear Hermitian operator. So now we have come to know what is the meaning of operator. Now we have to learn what is linear operator. Now linear operator, the definition is already given here. You can see an operator is said to be linear operator only when if it satisfies this condition. Okay, A, the operator A, when it is acting on two functions, okay, and basically the answer, the summation, when it is acting on the summation of the two functions, then that must be equal to when the same operator is acting on individually, and when you are adding together, that answer must be same. Okay, so how these left hand side and right hand side are basically different. You just take two functions, you just take any two functions, and then try to basically take the summation, and now you just allow your operator to operate upon f of x, on the summation of the two functions. Then okay, you will get some answer. Keep that answer aside. Now what you do, you have one function and you have operator. Okay, you allow A to operate first. In the right hand side, how this is different from this? Okay, you allow your operator A on to the first function. Similarly, you also allow your operator to operate upon the second function f2, and then you take the summation. You take the summation. If this number and if this number both are same, then we call the operator A as a linear operator. Okay. So this is very simple, that you can basically work out with the example what we have seen just now. The first example is that the first function f of 1, f1 is x square, the f2 is e to the power x square. And let us consider operator d by dx is equal to as an operator, right? So I'm taking two functions, and I'm considering d by dx as a operator. Then you can see here in this particular case, this is quite obvious that, okay, when d by dx is operating on the summation of the two function, will be precisely same as when it is acting on the individually on the two different functions and their summation of the individually when it is operating. Okay, isn't it? You can just do this. I'm not going to do work out this. It is quite obvious that, d by dx square. So what is the answer? You can just calculate. It is just the first derivative of the x square is the 2x plus the first derivative of this one. So there is some answer, right? That answer will be exactly this. Exactly this. Therefore, the operator A, that is d by dx, we call it as a linear operator. Okay. This condition, it looks like that it is quite obvious, but it is quite obvious, but it is not so. For example, you just take the condition, the same two functions, like x square is one function, the other function is e to the power minus 2x. Okay, and you take the operator x square. You take the basically not x square, square of the operator. Square is operator, right? We have done this. So now you take the f1 plus f2. Okay, this is the summation, and you take the square. And similarly, you take the square of the individual function, right? You take the square of the individual functions and then add them together. That is the another case, right? So when you do this, then the answer on the left hand side and right hand side precisely will not be the same. You can just verify it. Here, x square plus e to the power minus x squared, and then square of this one, actually, you know that a plus b whole square. A plus b whole square means a square plus b square plus 2ab is there. But on the right hand side, you can see here, you have only x square, that is like a square plus b square, but you don't have the additional term, right? Therefore, this condition is not fulfilled in this particular operator case. What is the condition? This condition. Okay, when a is operating on the summation of the two functions, which will not be same as then when a is acting on the f1 and then when a is acting on the f2. Similarly, the square root, you can take the square root function. Okay, square root as an operator. Square root is my operator. I'm just going to take the square root. Okay, now square root of f1 plus f2 definitely will not be same as the square root of x square plus square root of e to the power minus 2x, right? So that's all the explanation of linear operator. Okay, so now we have learned what is observable, and what is the operator, and what is linear operator. Now I'll come to the last condition, that is a Hermitian operator, linear Hermitian operator, right? So Hermitian operator is something very important thing in quantum mechanics, and then the definition of the Hermitian operator is basically is given in this particular slide. You can see here the operator A is said to be Hermitian operator only when if it satisfies this particular condition. Okay, so what is this? It is very simple. Okay, I am considering two acceptable wave functions. What are those two acceptable wave functions? One is a phi, the other one is psi. Phi and psi are my two acceptable wave functions. Okay, we can take it. So we just verify three conditions. What are those? The it must be square integrable, and then it must be a continuous function, and it must be a single valued. So any two such mathematical function, you can take it, no problem. Now what you do, you can take any operator. So you allow that operator to operate upon one function, that is psi. Okay, when an operator operates upon a function, what happens? You will get another function, right? We have just seen. Okay, when an operator operates upon a function, then it transforms to some new function, right? Now what I'm going to do next thing is that I'm going to multiply with the complex conjugate of the second function. What is this? Phi star. Phi star is complex conjugate. I'm sure that most of you would know this. What is the meaning of the complex conjugate? In the complex numbers, that whenever we come across I, we replace with what? What do you mean by complex conjugate? Can anybody answer?
We change the sign of I.
Yeah, so whenever you come across I, you have to replace with minus I. That's all. Okay, in the function, suppose uh, we begin describing phi is one function. Suppose if that function is having an I, imaginary that I, if it is there, then you just replace to get the complex conjugate of that particular function. Then you have to replace with minus I. Let's say, let me give an example. We have a function e to the power ix is a function. I hope that you all will agree, right? Now ix, if you want to get the e to the power ix, then if you want to get the complex conjugate of that one, then you have to replace minus I. That means e to the power minus ix is the complex conjugate of the e to the power of ix, right? That's all. Now having understood that, now come back to this. So what we have done here, that we have a operator, and then we allow the operator to operate upon one function, okay, that is psi. Then we are going to get some new function. Then that new function we are going to multiply with the complex conjugate, right? What you will get? It's going to be some other function, isn't it? You just apply with regard to the two functions f of f1 and f2, what we have seen in the previous two slides. F1 is x square, and then the f2 is e to the power minus 2x. That was the those are the two examples that I have given. Okay, you just apply these conditions, and then what ultimately you will be getting is that there will you will get a function. Okay, you will be getting some function, and that function, you just integrate that function and apply the limits, and apply the limits. The the limits are basically minus infinity to infinity, and what is the answer? You will basically, you are going to get some number, because integration, after doing the integration, you are going to get something, some numbers you are going to get, or some function you are going to get. Keep that thing aside. Now come to the other side. What is there? Okay, initially in the previously, we have basically allowed our operator a to first basically allowed a to operate upon the second function. But now what I'm saying, the same thing, the same operator, you allow it to operate upon phi, not instead of psi. Okay, you allow it to operate upon phi, and you are going to get some function from this operation, that you multiply with the complex conjugate of the second wave function, right? And then you are going to integrate it, and then apply the limits. Okay, you are going to get some function and take the complex conjugate. Okay, so don't be afraid of when you see the expressions or the equations. These are fairly simple, but unfortunately we make ourselves very complicated. But things are so simple, right? So what you do, in one case you allow your operator to operate on one function, and then multiply with the complex conjugate of the other function, and then integrate it, and then apply the limits. Ultimately you will get some answer, right? Similarly, the same thing you can do but then instead of allowing it to the first function, you allow it to the second function and multiply with the first function complex conjugate, and then integrate it, okay, and apply the limits, and then take the complex conjugate. If in your answer, if there is a I, then you replace with minus I, or if there is a minus I, then you replace with I. That's all. Okay, if the if the left hand side and right hand side answers are same, then basically we say the operator A is a Hermitian operator. Okay, so very in a very simple statement. Okay, A is said to be a Hermitian operator only if it satisfies this condition. I have given very lengthy explanation, but all the lengthy explanation is just to understand the equation. But you can just remember the definition. Any operator is said to be Hermitian operator only if it satisfies this condition. Okay, in this condition, I have used A as a notation, but you can use some H, Hamiltonian, or maybe some other notation, etc., etc. You can use it. It doesn't matter. But the only thing is that these conditions must be fulfilled, and this is the condition that we will be using very frequently in our discussions as we proceed in learning the quantum mechanics. Please remember this statement. Okay, now I will come back to the statement, the second half of the statement. So we have now come to know the first half of the statement we understood. So corresponding to every observable, there is a linear Hermitian operator. Okay, if you have a observable, the first half of the postulate, second postulate states that if you have a observable, then it will have a Hermitian operator. Okay. Suppose if you have a momentum is one observable, then it will have a Hermitian operator. Okay, and if you have a kinetic energy observable, then corresponding to kinetic energy you will have a Hermitian operator. And if you have a total energy, then for total energy there will be a Hermitian operator. So that is what the first half of the second postulate. Now the question is how to find the operator first. How to find the quantum mechanical operator. It is not the simple operator, but quantum mechanical, the operators are slightly different. Now to find the operator, the second half of the postulate states that to find the operator, one has to write down the classical mechanical expression for the observable and make the following replacements or changes. Okay, if you want to find the quantum mechanical operator, then what you have to do, you have to write down the classical mechanical expression first and then make two changes. What are the two changes? One is wherever you come across a variable x, then replace with x. If you come across a momentum px, then replace in the classical mechanical expression, then replace with minus ih cross dou by dou x. Okay, now this is for one dimension, but suppose if you have a three-dimensional system, it will have x component, y component, and z component. In such a scenario, then if you have a y in your classical mechanical expression, then you have to replace with the y itself to get the quantum mechanical operator. Okay, now suppose if you have a momentum, then momentum 1 you have to replace with the py. Whenever you see a py in the classical mechanical expression, then to get the quantum mechanical operator, one has to replace with minus ih cross dou by dou y. If it is z, then it will be minus ih cross dou by dou z. That's all. Okay, so this is for simple one dimension I have written, but these things can be extrapolated to the any dimension that we may think of. Okay, now I will just illustrate this. Okay, for a couple of classical observables and what are the quantum mechanical operators. Okay, so the first thing is position. Please remember position x. Okay, x is the position. So if a particle is moving in x direction, then its position is keep on changing, and the what it actually dictates, what is the variable that it tells us that the position is changing, then it is basically x. So to in the quantum mechanical, to get the position means x is the position. So wherever you see x, according to the our definition of the second postulate, whenever you see x, you have to get the quantum mechanical operator, then you have to just write down same x. You need not to do anything, which means basically you need not to do anything, just write down that. Then suppose if we have a momentum p of x, if there is a momentum p of x, then you have to replace with minus ih cross dou by dou x. Momentum px is the classical mechanical expression for a momentum. But in quantum mechanical, we don't write that. What we write is minus ih cross dou by dou x. Please note down. Then kinetic energy. The kinetic energy, I told you already, it is represented in a slightly different form than px square by 2m is the kinetic energy expression. Expression of the kinetic energy of a particle which is freely moving in one particular x direction is basically px square by 2m. Px square by 2m. Okay, what is m? M is the mass. Okay, it is basically a constant. Therefore, what I did actually to get the quantum mechanical operator, you can see here, I have written 1 over 2m, 1 by 2m outside the bracket, and then px square can be written as px multiplied by px, isn't it? 1 minute. Well, px square can be written as px multiplied by px, but 1 px means we have to make this substitution, right? So minus ih cross dou by dou x we have to write, but you have another dou by another px. Therefore, I have written minus ih cross dou by dou x multiplied by minus ih cross dou by dou x. And if you simplify this, actually, it is basically going to be minus h cross square by 2m multiplied by dou square upon dou x square minus h cross square by 2m dou square upon dou x square. How it has come? It's very simple. You can just see that there is a minus I and minus I. Minus minus plus and I square. What is I square?
Minus 1.
Minus 1. Minus 1.
Well, so it is minus 1. Therefore, minus is written here. And here there is a h cross square and there is a h cross. Sorry, h cross, h cross. Therefore, I have written h cross square. Isn't it? Okay. And dou square. Dou x, dou x, dou x square. That's all. So, the quantum mechanical operator of the kinetic energy expression, kinetic energy, okay, is basically minus h cross square by 2m dou square upon dou x square. Now suppose you are interested in the other dimensions, y component, then minus h cross square by 2m dou square upon dou y square. In z direction, then minus h cross square by 2m dou square upon dou z square. Okay, so kinetic energy is an observable, and according to the postulate number 2, corresponding to every observable, there is a linear Hermitian operator, right? To write down the quantum mechanical, to find the quantum mechanical operator, you have to make the two replacements. Whenever you see a position, then you just position, that is x. X you have to replace with x, y replace with y, z replace with z. And the momentum, whenever you come across, then you have to basically replace minus ih cross by dou x. And accordingly, the other components. Now let us go back, let us continue our discussion and try to see what is potential energy. Potential energy in classical mechanics, we just represent with V of x. Please remember, my discussion is only for one dimension, therefore I'm writing V of x. But then if it is a three-dimensional problem, then it will have a V of y, V of z as well, right? So potential energy is basically V of x. Now, according to to find the operator, quantum mechanical operator, what we should do? Whenever there is a x, replace with x, right? Whenever there is a momentum p of x, then it has to replace with minus I h cross by I h cross dou by dou x, multiplied by dou x, right? But here there is only x. Therefore, the quantum mechanical operator of potential energy remain the same. There is no change, right? Please note this. Suppose I may be interested in the total energy of the system. Total energy of the system is again one observable. And if you want to find the quantum mechanical operator for the total energy, then what you should do? You should do these two replacement, right? So let me write down. What is the total energy in classical mechanics? What is the total energy in expression in classical mechanics? The total energy is nothing but the kinetic energy plus potential energy. Okay, if a system is moving, then it will have a basically it will have a kinetic energy. And on the other hand, if it is basically in some kind of position, then it will have a potential energy. And if it is interacting with the system, there will be a potential energy. Therefore, the total energy is taken to be the kinetic energy plus potential energy. And the kinetic energy, classical mechanical expression for kinetic energy is p square upon 2m, px square upon 2m. And potential energy v of x, right? So basically this and this I have basically taken the summation. That's all. There is nothing new in this. Okay, this and this I have taken the summation for total energy. Then what will happen to quantum mechanical expression? You can see here the total energy operator in this case, right? Px already we have found what is the answer. I mean the kinetic energy operator, quantum mechanical operator, we already found. This is the answer, right? Minus h cross square by 2m dou square upon dou x square. Okay, this I have written plus v of x. Okay, now this particular thing, the total energy, kinetic energy plus potential energy is nothing but the total energy, and the total energy operator in quantum mechanics has a special name, and the special name is basically Hamiltonian. It is called as a Hamiltonian, and its conventional notation is the H. Okay, H, and then there is a hat on top of it. H, and there is a hat on top of it. Okay, and if you come across in some of the textbook, in a very fancy way, they will be writing, you can see here this type of symbol, and then there will be operator. Okay, so just to simplify things, I have just written here, but then if I'm writing in a board, I will be writing such kind of thing. But since it's a online PowerPoint, so I have just simplified, just I'm writing only H, but then that H and then this H is remain the same. It is just a notation. Why we are using such a notation? Because people, the so-called very renowned persons who developed this subject actually use that notation. We are just following that, but it doesn't mean that you should always follow that. But it is better that in the memory of so and so people, it is better to follow. So Hamiltonian is a person. Therefore, people started using that Hamiltonian operator in mathematics. Very nice thing. Hamiltonian space, Hilbert space. There are many things. So just to commemorate those people, it is they have started writing the Hamiltonian very fancy way in the H. Instead of writing simple H, so in a different way they write it. And don't confuse, it is just a notation. There is nothing different. The concept is something that is important. And you please note down, the total energy operator in quantum mechanics has a special name. What we call it as a Hamiltonian. Hamiltonian is the total energy operator in quantum mechanics. Okay. Now, this is for one dimension, and these are the quantum mechanical operators. Suppose if you extrapolate this discussion to a particle which is freely moving in a three-dimensional space. For example, you just recall the example what we have discussed in the previous class, that is yesterday class, while discussing the postulate number 1, for a three-dimensional system, right, there must be three different position coordinates and one time coordinate, right? So we can, I have given two example, like, the helium atom is moving in a space, in a room. Okay, you are in a room, then you just think of that it is moving in a space, and then to define its the position of the hydrogen atom or the helium atom, then you need a three position coordinates. Therefore, it is said to be three dimensional. Now, suppose if you are interested to find out the total energy operator for such a system, then what you will write? What you will write? Okay, what you will write? Very simple. Then we will have the XYZ components. We will have XYZ components. You can see here the kinetic energy initially, if it is moving one particular direction, then we normally take it as a px square by 2m. But if it is moving three dimension, then the three components we will be taking, and then this is the classical mechanical expression. This is the classical mechanical expression. Now, to get the quantum mechanical expression, what we should do? We have to make the replacements. Okay, IH cross minus IH cross by dou upon dou x square, right? Dou by dou x, yeah, dou by dou x we have to make it. Then when you make that, then we will basically get this type of answers. Okay, ultimately it is going to be minus h cross square by 2m multiplied by dou square upon dou x square, right, plus dou square upon dou y square plus dou square upon dou z square. Okay, so this is the x component. And you simplify it, when you make the substitution, minus IH cross square, IH cross dou by dou x, then you will get this answer. When you make the substitution minus IH cross dou by dou y, then you will get this answer. When you make the substitution minus IH cross dou by dou z, when you make that substitution here, then you will get this answer. So just to simplify and take the common terms outside, therefore you will get this answer. Okay, minus h cross square by 2m dou square upon dou x square plus dou square upon dou y square plus dou square upon dou z square. I hope that you all know what is exactly dou square upon dou x square plus dou square upon dou y square plus dou square upon dou z square. It is the Laplacian operator. It is referred to as the del square. Del square. Okay, so the Hamiltonian operator of a particle which is moving in a three-dimensional space is nothing but basically h cross square upon 2m multiplied by del square. H minus h cross square upon 2m multiplied by del square is the total energy operator, which we call it as a Hamiltonian operator of a particle which is moving in a three-dimensional space. Okay, so please note down. So this is a very simple thing. There is nothing much required to understand that. It's very fairly simple task. And well, I think the continuation is, suppose we have only considered the kinetic energy, but then we have not considered the potential energy. Suppose, if a system is basically in some kind of height, okay, it is not in the ground state, but then if it is somewhere above the ground, then naturally it will have a gravitational force. Therefore, accordingly, the potential energy term that we have to incorporate in the total energy. Okay, if it is moving freely, okay, there is a meaning actually. I have used earlier also the terminology. Please catch my words. There is a meaning, and whenever you don't understand, you just ask me. Free particle means it is moving freely and it is not interacting. So if it is not interacting, naturally it will not have any potential energy. So such a particle, if a particle is moving freely, it will have only kinetic energy. It will not have a potential energy. Okay, such a particle we call it as a free particle. Suppose if this particle is having some potential energy because of the height, let's say, um, maybe if it is elevated in an elevated position, elevated place, if the particle is there, our quantum mechanical particle, then it will have basically some kind of potential energy. In such a scenario, the total energy Hamiltonian operator will have the basically the potential energy term as well. Okay, so you know that mgh or the mg z. Z basically is the height of the system. But however, when you, as I have told you that we are dealing with the quantum mechanical particle, the mass of the particle is very small, isn't it? These are very small particles, and the mass is very negligible mass. Therefore, the potential energy term, which comes from the because of the position, normally we don't write it, but then in reality, the potential energy will be there because of its position. As you go above the ground, then we will have a gravitational force, right? Right. So mgh is the conventional, but then it is replaced with the mz. Basically, z represent the height of the particle, from the ground, right? So normally we don't write the gravitational potential, but then in reality that is there. In reality, theoretically, in principle, that is there. But in a general notation, we don't write because because the mass of the particles what we are dealing is very small. But there is another potential energy. It is possible. It's like, when it is interacting with the other particle, there is, Coulombic interactions. The attractive and repulsion forces will be there. Then that will lead to some the appropriate potentials. Those potential we consider. Okay, so that discussion will come in as we proceed learning things. But then right now, just the gravitational potential will not be there. Okay. So that's all about the second postulate. What is the time now?
5.
So what is your mindset? Will you be interested in learning a subject, or you want me to stop?
Today we have to stop because it's so conceptual. We have to repeat it again if I have to start that.
Pardon, who is that?
Sir Sahabuddin.
Shabuddin, you are saying something. What is that? Can you repeat again?
So, today we'll stop here, sir.
Why?
Because the postal we have to revise it because I'm little bit I taking some hard little bit here.
What's one you have to revise is therefore you don't want me to continue. Anyway. Okay, fine. Actually, I have thought to complete third postulate also. It requires maybe another half an hour to complete. In that case, maybe we will meet on Monday. Okay. Thank you. Bye bye.